Okay, we define a linear code as a k-dimensional vector space or subspace in FQ to the n. And one of the simple way to describe a specific code explicitly is to write down its basis. So we will write this basis by using what is called the generator matrix. This is going to be K by N matrix, whose rows form the basis for C. And if the generator matrix can be transformed applying after row reduced echelon, if its row reduced echelon form is the form of identity augmentation, a matrix A. In this case, the form of this matrix will be called the standard form of generator matrix. And another way to describe a linear code is to look at the solutions of some homogeneous linear systems. For instance, as a two example, we can also identify a linear code, for instance, length 5 over the binary field, such that whose coordinates are solutions of this given linear homogeneous system, or equivalent to bilinear algebra. We can say that if we write coefficients of the variables from x1 to x1 in a matrix, a linear code can be defined as the solution of this equation system. To describe it more formally, indeed we will introduce what is called first inner product on n-dimensional vector space. In the textbook, it is also called the canonical inner product on FQ to the n. Indeed, it is the same inner product which we are familiar in linear algebra. So that means it's going to be sum of the products of their coordinates. In the literature, you can also see some definitions, what's called Euclidean inner product. And we can easily check that in that it is non-degenerate, symmetric, and bilinear form on FQ to the n. And in the literature, you can also see various extensions of generalizations of this kind of inner products, or this kind of non-degenerate, symmetric, and bilinear form. But in this course, mainly we will consider the canonical inner product on FQ to the n. And here, even though it seems similar, the inner product, canonical inner product on the real numbers, it behaves in some sense different. For instance, if you consider the inner product on real numbers, we know that there is no vector which is orthogonal to itself. So that means their inner product is not zero, cannot be zero. But in the finite field case, we will see that, for instance, if we consider F2 square, with respect to this definition, we can easily check that the vector 1 is orthogonal to itself. So in the finite field case, we should be careful. And with respect to this inner product, we can define the orthogonal complement are vector space C. So that means if we are given a linear code C, then its orthogonal complement contains vectors U whose inner product is 0 with all codewords from C. And in the coding theory, this orthogonal complement will be called the dual of the linear code C with respect to Euclidean inner product. And here, indeed, we can easily see that if our linear code is a k-dimensional vector space, its dual will be n minus k dimensional vector space. And as more formal definition of this two example, or another version of which is also closely related to generator matrix, we will call the parity check matrix H of an NK linear code C, in that it will be the generator matrix of the dual code. N minus K times N matrix of rank N minus K, or indeed we can also describe a linear code which contains code words such that the multiplication of the given matrix H and the transpose of U, or equivalently from linear algebra, we can say that it contains some vectors whose multiplication with H transpose is 0. And obviously, you can see its relation with the generator matrix of C, or the generator matrix G. And depending on we mentioned that the inner product behaves different over finite fields. For instance, a vector can be orthogonal to itself with respect to Euclidean inner product. And in this case, let me call it remark and definition. And if a linear code is equal to its dual, then we call it self-dual. And it is called self-orthogonal if it lies in its dual. And these are indeed folklore definitions, but very recently, actually in 1992, another code family is defined, which is called linear complementary dual. Complementary dual or LCD. In short, if a code has trivial intersection with its dual. So that means we can also equivalently describe the linear complementary dual codes if they have direct sum, if the whole space can be written as a direct sum of the code C and its dual. My motivation to mention this code family, very recently in 2018, separately it was proved by Ruth Pelikan and Claude Carland et al. By applying some spatial transformations, indeed we can get, for a given nk code over Q, if Q is strictly bigger than 3, then there's a spatial transformation which gives us an LCD code. And equivalently, if you begin with an LCD code, you can also get a linear code. And I think this is quite important result in the characterizations of the linear codes.